Have you ever wondered how massive websites stay online, even when a physical data center halfway across the country catches fire and shuts down? Engineers use a design approach called fault tolerance. It hides broken, melting hardware from the people using the website, making sure the experience remains completely smooth, even during a disaster. To build these systems, we use redundancy. Imagine a student who knows their dog has a habit of chewing on paper, so they copy their final essay into 3 different physical notebooks. If one notebook gets ruined, the work survives safely in the others. By assuming that hardware will eventually break and preparing backups in advance, you can take a fragile system with a single point of failure and turn it into something that can survive almost anything. In software, that notebook strategy comes in 3 forms. First is information redundancy. A digital data packet attaches a small, locked badge to itself before it travels. This verification data proves the message wasn't scrambled or corrupted along the way. Then there is temporal redundancy. If a temporary network glitch stops a task, the system automatically runs the exact same process over and over again until the action finally succeeds. Finally, we have spatial redundancy. This involves taking your data and physically copying it to different server machines spread across separate cities or even different countries. Combining these 3 layers guarantees that your data is accurate, your actions are finished, and the loss of a single building never wipes out your work. A fire is easy to see, but it's much harder for a network to know when one of its own internal parts is quietly failing and delivering bad data. Imagine a talent show where a singer is performing on stage and 3 judges sit at a desk, carefully scoring the performance. 2 of the judges give the singer a solid 8 out of 10, but the 3rd judge's electronic scorecard malfunctions, showing totally scrambled, incorrect numbers compared to the others. If a computer network receives that kind of conflicting internal information without a built-in way to hold a vote, it freezes up and crashes. To solve this, we use triple modular redundancy. An incoming task is sent to 3 parallel server nodes simultaneously. They send results to a majority voter. 2 nodes send matching green results, while the broken node outputs a red packet. The voter incinerates the anomaly. This process is called fault masking. The healthy servers completely hide the broken one, so the overall system continues to work flawlessly for you. When you link whole groups of these servers together into clusters, they behave like a sports team managing player injuries. One method is the active-passive model. Think of this like having a star player on the court, while a backup player sits on the bench doing absolutely nothing unless the star gets hurt. This diagram shows that in action. A primary data center handles the traffic, but if it fails, a failover alert triggers a redirect. Traffic is sent to the standby server, which was previously just waiting on the bench. This model guarantees a safe backup is always ready, but it means buying expensive hardware that spends most of its time sitting completely idle. To get more out of the equipment, we use the active-active model. This is like putting your entire roster on the court at once, sharing the ball evenly so no single player gets exhausted. This chart shows how that works. On the left, a load balancer, which acts like a digital traffic director, takes every incoming request and splits it up between several proxies, which serve as the entry points to the system. For even bigger systems, you can use the N+M model. This gives you several active working servers supported by multiple dedicated bench servers, all waiting to swap in if the active group gets overwhelmed. These clusters ensure that no matter how big a traffic spike is, or which piece of hardware suddenly dies, the system never drops the ball. The world's most unbreakable systems don't rely on perfect hardware. They rely on voting out errors and acting as a redundant, unified team. Next time, we'll see how we organize these applications by packing computer systems into tiny, lightweight digital shipping boxes. Combining those digital boxes with the rules of redundancy allows you to build a version of the internet that simply cannot be broken.